Good afternoon, class. Here's Calculus 1 final exam review, the first part covering from section 2.1 to 6.1. So again, I can't emphasize this. Before starting the exam, please read the following pledge. I pledge on my honor that I will neither give nor receive unauthorized assistance during this exam. I just want to make sure that everybody understands the assumption is that you are taking an exam on your own as though you were in class. So I really can't emphasize this enough. It's important to know that, okay, in any event. So differentiation formulas, you should be very comfortable with. Differentials, delta y versus dy. Delta y is f of x plus delta x minus f of x. Dy is f prime of x dx, and delta y and dy are not the same. Delta y is rise along the curve, dy is along the tangent line. And if you find the tangent line, they will give you the same value. Logarithmic properties, as long as we know this, which means we can go to the exponential format. Therefore, all of these properties for a general form works nice and easy, as well as common log when the base is 10, as well as the natural log when the base is e. By the way, common log, we don't write the base 10, common and natural log, we write ln x. These are the properties. Exponential, logarithmic, they are inverse of each other, change of base formula, and the derivative of logs. Integration basically is the reverse process. That's all there is to it. Fundamental theorem of calculus, there are two parts. The derivative of the integral is the function itself, and the integral of a to b f of x dx is capital F of b minus f of a. And this is the definite integral, which represents a number, which represents difference of areas in general. If it's positive, it's the area under the curve. Otherwise, it could be the difference of areas. And substitution rule, f of g of x, g prime of x dx, where g of x is u, is integral of f of u du. And again, I can't emphasize this enough. I expect students to do the u substitution, okay? That's what we cover, okay. Let's go from the get-go, okay, what we have covered from the beginning. And that would be the synopsis we're going to cover to get ready for the final exam. And again, I'm emphasized to get ready for the final exam, all you have to do just master the previous. Given the graph of a function, g, state the value if they exist. So we're interested in the limit of g of x as x approaches 2, and that's why we look at one-sided limit. The limit, by definition, remember, the limit of f of x as x approaches a from the left equals L. The limit of f of x as x approaches a from the right is L. Then the limit does exist. So we want number 2. If you come from the left of it, you're going this way, and you're moving towards this hole, which has the y coordinate 3. But from the right side of number 2, you're moving this way, which means you're moving towards this hole, which has a different y coordinate 1. Since they are different, the limit doesn't exist. What about number 5? Again, we're going to look at one-sided limits. And from the left, we are here. From the right, we are here. And in both cases, we are moving towards this hole. Remember, when it comes to the limit, we never get there. And so the answer is the same, namely 2 in all cases. Because the left and right are identical, as far as the limit is concerned, the limit does exist. Now, let's assume this point has a y coordinate 1.4, which indicates the functional value is 1.4. G of 5 is 1.4, but it's not equal to the limit. So it still makes it discontinuous, because The definition of a continuity indicates limit of f of x as x approaches a equals f of a. In other words, the limit and the functional value are identical. The limit does exist, otherwise it doesn't. So g of x can be continuous at x equals 5 if we just redefine it, because this is a removable discontinuity. Just all you have to do, fix this by redefining the functional value to be equal to the limit. Because the limit exists, we can fix it. In other words, if the limit exists, it's fixable, it's removable. However, this one, there is nothing we can do to fix it because the limit does not exist. It's a jump, and there is no way to fix it. So that's the difference between the two. All right. Now, in this case, we want to find the limit of this function at various points, reminding everybody about VA, namely vertical asymptotes. The limit of f of x as x approaches a, or a from the left, or a from the right, it's positive or negative infinity, indicates VA, vertical asymptote, has the equation x equals a. So approaching 2, I hope you see in both sides, we're going to go towards negative infinity. Number 5, both sides takes us up to infinity. And in the case of negative 3, well, it depends. From the left, negative infinity. From the right, we're going up to infinity. And that means that x equals 2, x equals 5, x equals, these two mean the same thing. X equals negative 3 would be our vertical asymptotes by definition of a vertical asymptote. How do we find limits? Just plug in and observe. It gives you a number, you're done. It gives you 0 over some number. Remember, by that we mean nothing. Any number is fine except 0. The result is 0. If it's some number over 0, it's infinity or negative infinity. But in calculus, we end up mostly with indeterminate forms, and there are many different types. For example, 0 over 0, infinity over infinity, or infinity minus infinity. Those are some of those in the indeterminate forms. All right, so we are dealing with the following: limit of 2x squared plus 8x over x squared minus 16 as x approaches infinity. So you're dealing with a rational function. Even a fractional format follows the same. And x is approaching infinity, my apologies. Therefore, the methodology is to divide by highest degree term in the denominator, namely x squared. So divide everything by x squared. So because x is approaching infinity, divide by x squared. When we do that, this becomes obviously 2, this becomes 1, this 8 over x minus 16 over x squared. Because x approaching infinity, this goes to 0, this goes to 0, the answer is simply 2. However, the really base course of action is to simplify if you can. So we can factor, and notice the numerator is 2x times x plus 4. The bottom is x plus 4x minus 4. You can cancel out the x plus 4. And the answer is 2x over x minus 4. All of this stuff we've covered already, so that's why we're going over this pretty fast. So if we were to deal with the factored form, this time we would divide by x. And the result is the same too. Now, definitely when you are dealing with a fractional format, it's easier to go with the factored form. Remember, I'm going to use the same expression. So let's deal with the factored form. And by the way, if you plug in, you do get 0 over 0. And so factored form gives us the limit as x approaches negative 4 of 2x over x minus 4. So if I plug in -4, the numerator becomes -8. This becomes -4, which is also -8, and it's equal to 1. This one, again, it so happened if you plug in 0, everybody, the numerator becomes 0, and the denominator is -16. So the answer is 0. It just works out. But it's really not a bad idea to work with the factored form, in which case gives you 2 times 0. So let me just write that because I want to make sure that you see that the answer is 0 in the numerator, -4 in the denominator, therefore it's 0. Now, finally, for this page, I want to look at both of these cases together. And again, I want to go with the factored form in both cases. Now, x is approaching 4 from the left or from the right really doesn't make much of a difference for the numerator. The numerator is 8 in both cases, everybody. Now, let me be clear. 4 from the left like 3.999 or 4 from the right like 4.0001. The numerator is 8. The denominator, if you plug in 4, you get 0. 0 is the only number, everybody. The right side is positive. The left side is negative. And for 0, you have to figure out it's from the left or right. Therefore, for this one, if you plug in, you get 4 from the left, let's say 3.9 minus 4, you get minus 0.1, 8 over 0 from the left, whereas here, like 4.1 minus 4 is 0.1, so 0 from the right. So the difference is, in this case, positive over negative gives you negative, negative infinity. In this case, positive over positive is infinity. So both of them are infinity, but you have to figure out the sign. This one is negative infinity. And the fastest and easiest way to figure it out is the way that I just went over for you. All right, t is approaching infinity. We want to find this limit, plug in, and notice a to the power minus m is 1 over a to the power of m. Therefore, e to the power minus t is 1 over e to the power of t. And that's what happens here. And this becomes 0 because this is e to the power minus infinity, which is 1 over e to the power of infinity, which is 0. And therefore, the answer is 3. In this case, if you plug in, e to the power of t becomes e to the power of infinity or infinity. The numerator, if you multiply infinity by any number, as long as it's positive, is still infinity, and the result is 0. And I hope you see that part C works out being identical to part A because this is e to the power minus t, and t is approaching infinity. This is e to the power of t, but t is approaching negative infinity, and we get exactly the same answer. What about this last one? Just replace the t with 0. As you know, e to the power of 0 is 1. So we get 3 and 4, 7. So 12 over 7. Notice, again, I put all these questions next to each other because it's really a good practice to see them side by side. And let's switch gears, differentiate. And as you recall, we want to differentiate. We bring, if you have a number, just a number in the numerator, bring the bottom up always, and you don't have to go with the quotient rule. So what is the derivative now? We use the extended power rule. 12 remains, and then times, so now it's n minus 1. And then the same thing to the power of n minus 1, minus 1, minus 1, or minus 2. And then the derivative of the inside 3 to the power of t. And you put all of this together. This goes down and takes a positive 2 as the exponent. 12 minus 1 and 3 e to the power of t minus 36 e to the power of t would be the numerator, everybody. All right, let's see what happens here. If you let x go to infinity, this becomes infinity, this becomes 0, infinity. So you get infinity over infinity. So it's indeterminate. What is the technique? Well, you're dealing with a fractional format. Granted, it's not a rational function, but it's a fractional format. And x is approaching infinity. And that's really the key. Because x is approaching infinity, remember, in the case of a rational function, you divide by highest degree term in the denominator. In this case, you divide by highest value. E to the power of 3x is the largest value. So let's divide everything by that. So what happens when we do that? This one divided by this one is 1, this one by this one is 1. But when you do divide this one, I hope you realize e to the power minus 6x. Class, this division is e to the power minus 3x over e to the power of 3x is e to the power minus 3x minus 3x gives you e to the power minus. And because x is approaching infinity, okay, this goes to 0. So you get 1. If you plug in x equals -4, you get 0 over 0. You have a complex fraction. The technique is LCD, least common denominator, which is 4 times x. First, I want to discuss the denominator. Remember, x is approaching -4. X plus 4 is a problem. You don't want to distribute. You want to get rid of that. You're hoping. So the denominator remains. Multiply these two. Multiply these two. You get x plus 4 in the numerator. And if you plug in, you get -1 over 60. Same thing with part C. If you plug in, you get 0 over 0. And that means we have to multiply by the conjugate, which is the same thing with the plus here. So we're going to multiply and divide by it because a, let me just write it here, a minus b times a plus b is a squared minus b squared, which means this will be 1 plus h squared minus 1 squared. And the denominator, you just don't touch it, it's a product. This comes out minus 1. And so 1 and -1 cancel each other. H and H cancel each other. And now if you plug in 0, this becomes 1 and 1 is 2. So 1/2 is the final answer. G of x is a piecewise defined function, half of x plus 3 when x is less than -2 and x minus 1 for x larger than or equal to -2. Is G of x continuous at x equals -2, y or y? Again, I've mentioned that before. Each piece is a linear function and it's continuous from negative to positive infinity. That's why you check the endpoint and definition of a continuity. So we start with the functional value. The functional value takes the equality. So we're going to use x minus 1 and plug in -2, which is also -3. Now we look at one-sided limit. We start with the left side, and left side uses less than. We're going to use this piece and plug in -2. Half of -2, -1 plus 3 is 2. Now what about the other side, the right side limit? We use larger than. We use the second piece and evaluate it, and we get -3. Obviously, the left and right have different limits. The limit doesn't exist. If the limit doesn't exist, it's not continuous either. So the limit is not the same. The limit of g of x doesn't exist. Therefore, g is not continuous at x equals -2. Now, notice these two are the same. Therefore, the question is it continuous at x equals -2 from the right? This one, this value, which is the functional value, and the right side limit, they are the same. The answer is yes here. But again, it doesn't change the fact that it's not continuous at x equals -2. Okay. Limit of cosecant x, sine of sine x as x approaches 0. And we're going to go for the beginning. Remember, the limit of sine theta over theta as theta approaches 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 is 0. So we're going to use one of those. And we notice that cosecant is 1 over sine. So we write it in this fashion. Now, it's important to know that x is approaching. So if you let sine x be theta, okay, since x goes to 0, theta equals sine x goes to 0. Sine of 0 is 0. It's important. If you want to use this theorem, this one, and this one must be identical. And the answer is okay. What about the limit of sine x squared over x as x approaches 0? We can rewrite this in the following manner. Remember, this must be identical to this, identical to that to use this one. So let's make it so. How? It's very simple. Let's multiply the top and the bottom by x. If I multiply this by x, that takes care of the x squared here. So this is identical to this. So now we can look at two pieces. Limit of this piece, x as x approaches 0, and limit of this piece, sine x squared over x squared as x approaches 0. Please understand, when x approaches 0, so does x squared. And because this one and this one and this one are identical, this whole thing is 1. The other one is 0. 0 times 1 is 0. So that's the justification for this. Very straightforward, everybody. If g of x is between 2x and x to the power of 4 minus x squared plus 2 for all x, evaluate the limit of g of x as x approaches 1, reminding you of the squeeze theorem. According to the squeeze theorem, if f of x is less than or equal to g of x less than h of x, when x is near a, except possibly at a, and limit of f of x as x approaches a equals limit of h of x as x approaches a equals l, then limit of g of x as x approaches a is l, meaning just find the limit of the left and right. If you happen to come up with the same answer, the middle one must have the same answer. So let's take the limit of this one as x approaches 1, and clearly the answer is 2. Let's do the same thing here. So 1 to the power of 4 is 1, minus 1 squared is 1. They cancel each other. The answer is 2. And because they are identical, the limit of g of x must be the same by the squeeze theorem. You have to mention squeeze theorem. You can't say this limit is equal to 2 and you're done. You have to write by the squeeze theorem. When proving certain limits become difficult, think of the squeeze theorem. And we are saying the limit as x approaches 0 from the right of square root of x, brackets 1 plus sine squared 2 power x equal to 0. There is a trick involved. And recall that sine is between -1 and 1. Sine of anything, alpha, beta, gamma, including 2 power x. So sine is between -1 and 1. Now, if you square it, it's important to understand it's between 0 and 1. You square this number, but this goes to 0. Let me go with some other numbers. I want to make a point here. If, let's say, just for the sake of argument, some expression, if x is between, let's say, -5 and 7, if you square it, obviously this becomes 49, but you can't say, I'm going to square this and it becomes 25. You have to go with 0. And here's the reason. Because as this number gets closer and closer to 0, between -5 and 0, when you square it, gets closer and closer to 0. So negative number, when you square it, on the negative side, you keep it 0. Not that it becomes 0, but by the nature that it's between -1 and 0. And so with that being the case, this becomes square root of 1 squared is the same. If it was 7, it would be 49. And so that's what we have. We want to make this a bracket. So let's add 1 to all sides. So this becomes 1, this becomes 2, and this becomes what you have inside the brackets. Notice this is the brackets. So everything is good. What is missing? Square root of x. Let's multiply by it. And because x is approaching 0 from the right, square root of x is positive, then this doesn't change. Remember, in the case of an inequality, multiplication and division by a negative number flips over the sign. In this case, it won't. So this becomes square root of x. This becomes 2 square root of x. And in the middle is exactly what you were looking for. Now we look at the limit of this guy and this guy, both of them as x approaches 0 from the right. And obviously, both of them result in 0. Because each one gives you 0, then the limit of this expression by the squeeze theorem must be 0. So the limit as x approaches 0 from the right of the square root of x bracket 1 plus sine squared 2 pi over x must be 0 by the squeeze theorem. I want to find this limit. It's important to know when you're dealing with roots, you are either dealing with, roots that have index, which is even or odd. If it's odd, you really don't have much to worry about. Negative comes out, positive comes out. But if it's even, it's a different story. Remember that. And we want to discuss that. So first of all, I'm going to take x to the power of 6 out. Again, this is one technique that will do the job. But how do I get this x to the power of 6 out? This is what I want to discuss. And so that means in case of the limit as x approaches infinity for x larger than or equal to larger than 0. Remember that square root of x squared is not equal to x, is equal to absolute value of x. And it becomes x if x is positive. But if x goes to negative infinity is minus x, because minus x doesn't mean negative, it means the opposite of x. If x is negative, then you go with the opposite of x. That's the meaning of absolute value. And x to the power of 6, it works out in the same manner. It's an absolute value of x cubed. So square root of x to the power of 6 is absolute value of x cubed. If x is positive, you can drop the absolute value. But if it's negative, it becomes minus x cubed. So if I want to drop this, I have to go with minus. And that's the idea, everybody. And I put it in a different color so you can see that. Now, because x is approaching, whether infinity or negative infinity, the methodology is the same. You divide by highest degree term in the denominator, which is x cubed. So if you divide the bottom, let's discuss the bottom, by x cubed, you get 2 over x cubed minus 1. And the numerator you divide by x cubed, this goes away. So this goes away. This becomes 2 over x cubed. This is minus 1. Because x approaching, whether infinity or negative infinity makes no difference. This is 0, so is this one. So you get minus square root of 0 plus 4. This is 2, so minus 2, and this is minus 1, and it becomes positive 2. So to recap, If the index is even, the answer is absolute value of x. If it's approaching infinity is x. If it's negative infinity is minus x. The same thing happens here. And you want to be very careful of that, everybody. Let's differentiate, and clearly 1 plus sine x over x plus cosine x uses the quotient rule. Let's call it f over g, and we're going to go f prime g minus g prime f over g squared. So what is f prime? The derivative of the numerator is cosine times g, which is the bottom x plus cosine x, minus g prime. Now this gives you what? 1 minus sine x, and then times f. Just put the numerator. Then the bottom, don't do anything. Put it in a parenthesis and square it. And keep it in this form. Now all we have to do is simplify the numerator. This is x cosine x. This is plus cosine squared. And this 2 a minus ba plus b equals a squared minus b squared, or 1 minus sine squared. And so this is fine, this is fine, this is fine. And I hope you remember that this is cosine squared by Pythagorean theorem. Sine squared plus cosine squared equals 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. If you look at this one, that means 1 minus sine squared is cosine squared. 1 minus cosine squared is sine squared. So clearly this one is cosine squared, and these two cancel each other. And we are done. Exponentials. The derivative of e to the power of x is itself. The derivative of e to the power of kx is itself times k. So this, the answer is itself. Just quickly, let's write it. So y prime is itself. Now, by the chain rule times 5. So in essence, we're using this. Same thing for this one, and we are using this. E to the power of tan x is itself. By the chain rule times the derivative of tangent, which is secant squared. This one, again, is the same thing, but I want to make sure that we understand this means 2/3 x. So the answer is itself, and then times 2/3. We put the 2/3 first. Now, what happens when the base is not the same? First of all, the answer is itself. Always the answer is itself. But if the base is not e by the logarithmic properties, we multiply by ln b, so we multiply by ln 3, and we rewrite it. What about here? First, the answer is itself, because it's an exponential. Then, is the base e? No, so we need ln b. Then is this x? No, it's a function of x. We need g prime times 7, and we rewrite it. Anytime the numerator is just a number, make sure you bring this up. X squared plus 3 to the power of -1/2, so 4 times that. This way, you don't have to use the quotient rule, okay? Not that you should avoid. For example, in example 10, we had no choice but to use it. And You don't want to avoid that, okay? When you don't have to, it's a different story. So what's the answer? 4. Now, extended power rule, -1/2. Same thing, to the power of -1/2 minus 1, which is -3/2. The derivative of the inside, which makes it 2x, and we are done with calculus. And now 4 and -1/2 is -2. With this one makes it -4x. And this is, of course, -3/2. So take this down, make it +3/2. So +3/2, or you can write it in the form of a root, either base form. What about 3x times 3 to the power of x? Again, product rule. F prime is 3 times g, which is 3 to the power of x, plus now g prime. The derivative of any exponential, first, it's itself. Then you look at the base, because it's not e ln 3. You're done with that. Now times f 3x. So f prime g plus g prime f. I'm going to erase my work. I want to show you something. Well, maybe I don't need to. So this is to the power of 1. This is 3 to the power of x plus 1, or 1 plus x. This, let me just erase my work. So this is to the power of 1, this 1 plus x. This one and this one give you the same thing. This is 3 to the power of x plus 1. And ln 3 remains. X remains. This 3 and this one give you the same. So if I take this one out, this one gives me 1, this one gives me x ln 3. Notice I put the x in front, because if you put it in the back, one may read this as ln of 3x, which is incorrect. So pretty straightforward. All right. The easiest way, anytime you have a fractional format, can I simplify it? And the answer is yes. This gives you x, this gives you 4. In other words, make up 2 fractions. This one and this one. And now differentiate. Y prime is simply 6. X plus 4 to the power of 5 times the derivative of the inside is 1. So I'm not going to bother with that. Now this obviously uses the extended power rule. First we have 5. Then we have the same thing to the power of 4. And now we're going to differentiate this. Using the quotient rule, f prime g minus g prime f over g squared. So f prime, that would be 2 times x minus 8. G prime would be 1 times 2x plus 3, so minus 1 times 2x plus 3. And just write it here and square it. So practically you're done. As far as calculus is concerned, you're done. And now you're going to do algebra. This is 2x minus 16 minus 2x minus 3. Clearly 2x and minus 2x cancel each other. It needs to add up to -90. So you can do it in one shot, but I do it in 2 shots. I want to make sure you don't make a mistake, because some students did make a mistake with the exam. So we have 5. We have 2x plus 3 to the power of 4. X minus 8 to the power of 4. Pay attention to the way we separate them. And the last piece we just write. The reason I do it this way, so you can see x minus 8 to the power of 4 plus 2 would be the denominator. 5 times negative 19 is negative 95, and 2x plus 3 to the power. We want to differentiate implicitly, and this uses the product rule. F prime g plus g prime f. So 4x squared gives you 8x times y, and y gives you y prime or dy dx. So times 4x squared. Now 2y squared is simply 4y y prime or dy dx. E is a number that gives you 0. We're done with calculus. We're going to put these two together. We're going to move this. So when we put these two together, we can take the 4y prime as a common factor out. So we get x squared plus y. This moves becomes negative. And all you have to do, divide by 4 times x squared plus y. These two cancel each other. They give us negative 2. Remember, when we deal with sinusoidal function, I've mentioned that the way I deal with it, I just read and I pause, cosine, and I stop. Cosine, the derivative is negative sine. But negative sine of what? You have to have the same argument. Whatever this is, you have to have it. And if this argument is x or t or theta, you're done. But it's not. By the chain rule, now you need its derivative, which is 12t cubed. This is the chain rule, everybody. And just put it in front, and the final answer is negative 12t cubed with the sine of 3t to the power of 4. Y equals tan to the power of 10 of sine of x cubed. And to make sure we know what we're dealing with, let's write this as tan to the power of 10. And in fact, I'm going to call this u. So u to the power of 10 gives you 10 u to the power of 9 du dx. So it's 10 u to the power of 9, 10 tan to the power of 9. Of course, of the same thing, right? 10 u to the power of 9, u is tan of sine x cubed. Now, du dx means take the derivative of a tangent, okay? So this one, I want to take the derivative. The derivative of tangent. First, I start with tan. The derivative is secant squared. The derivative of tan is secant. So secant squared of what? The same thing. Then I need the derivative of sine of x cubed. The derivative of sine is cosine. So cosine x cubed. Then I need the derivative of x cubed, 3x squared. I hope you realize it's the chain rule being used repeatedly. And then we put them together. Of course, 3x squared and 10 is 30x squared goes to the front. It's a good idea to put cosine x cubed in front, and then the rest in any order you like, and you're done. And this is it.